As shown in figure, a rectangular loop of width L is suspended from the insulated hook of spring. A current I flows in the anti-clockwise direction in the loop. A magnetic field B exists in the lower region. What will be the change in the tension of the spring if the current in the loop is reversed? So we are asked to find the change in tension in the spring if the current in the loop is reversed. And let me write this way, okay? We have current, okay, in anti-clockwise direction, and this is given, okay? And we need to consider, okay, current in clockwise direction also. So we need to consider current in clockwise direction also. So we have to find tension, okay? We need to find tension in this case. We need to find tension in this case. Let us tell or call tension in this case, that is when current is in anti-clockwise direction, is T1, and let tension, okay, in this case, that is when current is in clockwise direction, is T2. So we need to find the change in tension. Okay, so we have to find the change in tension, that is delta T. So we need to find this. Now let us come back to this figure, okay? So we can see we have a rectangular loop of width L. So the width is L. So we have this, okay? And current I flows in anti-clockwise direction. So current flows in anti-clock or anti-clockwise direction. So we have this, okay? So let me denote in this way, okay? We have current I flowing in anti-clockwise direction. So we have current flowing in anti-clockwise direction, okay? So we have this. Now, a magnetic field B exists in the lower region. So we have magnetic field in the lower region, okay? So in upper region, okay, magnetic field is 0. So we have magnetic field in the lower region. So this cross, okay, represent, okay, this cross represent magnetic field, and it indicate that magnetic field is perpendicular to the plane of the rectangular loop and is directed inward, okay? So we can see, okay, magnetic field. So it represent magnetic field. So let us denote, okay, magnetic field by this symbol. So we can see we have magnetic field represented by symbol vector B. So magnetic field is perpendicular to the plane of loop or board, okay, and is directed, okay, and is directed inward. So we have this, okay. Now, as I said earlier, we need to find the change in tension of the spring if the current in the loop is reversed. Now what we do, okay, we can see in the upper region, we have spring balance, okay. We have spring balance with insulated hook. The hook is insulated, okay. Now, in order to solve this numerical problem, okay, so I'm writing over here in this way. To solve this numerical problem, we use the concept of force experienced by current carrying conductor in the presence of magnetic field, okay. So I'm writing over here, force experienced by current carrying conductor in the presence of magnetic field. And the force, okay, let us denote it by this symbol. So force equals current element cross magnetic field, okay, cross product of current element and magnetic field. So we have this. Now direction of this force, okay, direction of this force is given by Fleming's left hand rule. So we have this. So in magnitude, I can write this expression, okay, in this way. Okay, in magnitude, force F equals I L, okay, this is current element, B sine theta. So we have this, okay, and theta, what is theta? Theta is angle between, okay, it is angle between current element and magnetic field. So we have this. So we are going to use this concept, okay, force experienced by current carrying conductor in the presence of magnetic field. Now let us name this rectangular coil, okay. So we have PQ, we have arm PQ or side PQ, and let us call this as R, okay, and this as S. So we have this. So we have now rectangular coil PQRS. So I'm naming, okay, this as rectangular coil PQRS. Now what do we find, okay, for arm RS, okay. Let's consider this first. What we find for this arm, okay, we find current flowing along this direction from R to S. And since we find magnetic field acting in the lower region, okay, magnetic field is acting in the lower region, there is no magnetic field, okay, that is arm RS is not in the presence of magnetic field. Even though it is carrying current, it is not in the presence of magnetic field. So I'm writing over here, this arm RS is not inside magnetic field. Therefore, arm RS experiences no force, okay, it experiences no force. So this is to be noted, okay. So we do not find force for the arm RS even though it is carrying current I, because it is not inside the magnetic field. Clear? So we have this. Now we go for arm QR and SP, okay. Now for arms QR and SP, so what we find? We find length of QR equals length of SP, and both are carrying, okay, both QR and SP are carrying equal current. So this is, okay, from the equation, okay, we can see this from the equation. Clear? They are carrying equal current, okay, in magnitude. Clear? So we have this. So we have this, okay. This is arm QR. It is carrying current I in upward direction, and it is inside the magnetic field. So this is very important point, okay. So we have this. It is completely inside the magnetic field. And for arm SP, okay, it is carrying equal amount of current in magnitude, but in opposite direction. So current is flowing in downward direction, and arm SP is completely inside the magnetic field, okay. It is completely inside the magnetic field. Now, what we do, we use this concept. As I said earlier, we use this concept, okay. So arm QR will experience force in the presence of magnetic field, okay, and it is carrying current I in upward direction. In same way, arm SP carrying current I in downward direction in the presence of magnetic field acting in inward direction will experience a force. And in order to find the direction of force, okay, we use Fleming left hand rule. So what is the magnitude, okay? Since we have length of QR equals length of SP, and they are carrying equal amount of current, okay, in magnitude. So we find, okay, magnitude of force, the magnitude of force experienced by arm QR and SP is same, okay. So I'm writing in this way. They experience same amount of force in magnitude. Now let us find the direction, okay, of force experienced by QR. So we use Fleming's left hand rule. So I'm taking my left hand, okay. I'm taking my left hand, and the first finger or index finger of my left hand, I'm pointing this finger, okay, along the direction of magnetic field, and magnetic field is acting in inward direction, okay. And my central finger, okay, central finger gives the direction of current, and current is flowing in upward direction. And the thumb, okay, the stretched thumb gives the direction of force. So this arm QR will experience force in this direction. So we have this, okay. Clear? Magnetic field is acting in inward direction, and the first finger is pointing along the direction of magnetic field, and the central finger is pointing along the direction of current, okay. Clear? And the thumb gives the direction of force. So force experienced by QR is along this direction. It is towards SP. Now let us find the direction of force experienced by SP, okay. So again, I use Fleming left hand rule. My first finger gives the direction of magnetic field, and magnetic field is acting in inward direction. And central finger, okay, it gives the direction of current. So current is acting in downward direction, and the thumb gives the direction of force. So we can see force experienced by SP is along this direction, okay. So we have this. Clear? So we find this arm, that is arm SP, will experience force towards RQ or QR. So we find force are acting, okay, along this direction and along this direction. And as I said earlier, magnitude of these two forces, they are equal and they are opposite in direction, because we know the expression for force is this, okay. We find B is same, okay, it is same, and the length of arm QR and SP is same, and they are carrying equal amount of current. So they experience equal amount of force in magnitude, and the force are opposite in direction, so that these two force, okay, these two force, they cancel, okay, they cancel out. So we have this. So in rectangular coil PQRS, we find no force act on the arm RS, and force acting on arm QR and SP, they cancel out. So I'm writing over here. Okay. Force acting on arm QR and SP cancel out. Okay. And next, no force act or acts on arm RS. Why? Because magnetic field is 0 in the upper region. So we have this. So this is to be noted. Okay. We have this. Now, for arm PQ, okay, let's say we find arm PQ or side PQ is completely inside the magnetic field. It is completely inside the magnetic field and is carrying current I along this direction. So we have this. So the arm PQ will experience force. So force experience by arm PQ is F equals current element cross magnetic field. Okay. As I said earlier, magnetic field vector B is perpendicular to the plane of the rectangular loop or plane of the board and is directed inward. Okay. And the length of PQ is L. Clear? So what do we find? We find angle between, okay, in this case, we find angle, that is theta equals 90 degree. Okay. So we find, or we can write in this way. We can write in this way. Let me write directly. Okay. Since angle between current element and magnetic field is 90 degree. Okay. Therefore, we can write in this way. So we have force experienced by arm PQ, that is F equals ILB. So this is in magnitude. Okay. So this gives me the magnitude. Okay. This is in magnitude. So we need to find its direction. Okay. We need to find its direction. Now, in order to find the direction, okay, in order to find the direction of this force, as I said earlier, we use Fleming's left hand rule. So what we do, okay, we take left hand, and as I said earlier, first finger, okay, we take first finger in the direction of magnetic field, and magnetic field is acting perpendicular to the plane of the board and is directed inward, and central finger, okay, this finger gives the direction of current. So I'm taking current along this direction, okay, along this finger, okay, and the thumb, stress thumb gives the direction of force. So what we find, thumb is acting in upward direction, so that direction of this force, okay, this force is upward, okay. So we have force acting in upward direction. So we have this. Clear? Now, the weight, okay, of arm PQ act in downward direction. We know weight always acts vertically downward direction. So let me represent, okay, this figure in this diagram. So what do we find? Okay, since current is flowing in anti-clockwise direction, okay, so we have this case. Okay, current in anti-clockwise direction. Clear? So we have this. We have current. So let me write over here. I in anti-clockwise, okay? I in anti-clockwise direction. So we have current in anti-clockwise direction. So this is to be noted, okay? We have this. I in anti-clockwise direction. So we find force acting in upward direction and weight acting vertically downward. Okay, we have this. And let us take tension, okay? T1 in this case. So I'm writing over here because we need to find the change in tension. Okay, change in tension of the spring if the current in the loop is reversed. So let me write in this way. Let T1, okay, this is tension in the spring when current in the loop is anti-clockwise. And we know tension always act, okay, in the string towards the point of suspension. So this is the point of suspension, okay. This is the point of suspension of the spring. So tension always act in the spring, okay, towards the point of suspension. So we find this. Okay. So what we find from this diagram, okay, we find T1, that is tension in the spring when current is in anti-clockwise direction. T1 plus, I'm writing in this way, okay, F force, I'm writing in magnitude. This equals mg. Clear? Now T1 equals mg minus, okay, F, and the value of F is ILB. So we have this. So this is the value of force, okay. So we have this. Let us call it, this is equation 1, okay. Let us call it equation 1. So we have this. This is equation 1. Now, next, okay, when current in loop is reversed, that is I, current I in clockwise direction. So we have this, okay. So in this case, okay, let T2 be the tension, okay, in the spring when current is in clockwise direction. So we have this, okay. So let me draw the diagram, okay. So we have this, okay. This is P, Q, and this is R, S, okay. I have supposed this. Now we have current in clockwise direction. So current is flowing along this direction, okay. It is flowing in clockwise direction. So we have this current in clockwise direction. We have this, okay, current in clockwise direction. And from the question, okay, what we find, clear? Magnetic field B exists in the lower region, okay. So we have magnetic field B in the lower region only. So magnetic field in this region, okay, this is 0. In this region, okay, magnetic field is 0. In upper region, magnetic field is 0. So we have magnetic field only in the lower region. So we have this. Clear? So as we did earlier, okay, arm RS, okay, will not experience force. So this is to be noted, okay, as we did earlier, since there is no magnetic field or the arm RS is not inside the magnetic field, so it will not experience force. So this is to be noted, okay. And we can see force on arms, okay, SP and QR, as we did earlier, cancel out. So we have this. Now for arm PQ, so we have this. We have PQ and its length is L, okay, and it is carrying current I in this direction, that is from Q to P, and the arm PQ is completely inside the magnetic field, okay. It is completely inside the magnetic field B, which is perpendicular to the plane of the board or rectangular loop and is directed inward. Now the force experience, okay, force experience by arm PQ is this, okay. So we have this. So F equals this, okay. And as we did earlier, angle between current element and magnetic field, okay, we can see angle between current element. So I can take small current element, okay. I can take small current element, okay. It is horizontal. So this is current element, okay, small current element, and current element is acting along this direction, okay, and magnetic field is directed inward. So magnetic field is directed inward. It is perpendicular to the plane of the board and is directed inward. So angle between magnetic field and current element. Okay, this is current element. So the angle is 90 degree. So we can write F equals ILB. Why? Because theta is 90 degree. Okay, this is to be noted. Clear? Now, what we find, we are getting the same value of force in magnitude for the arm PQ when current is flowing in anti-clockwise direction and in clockwise direction. Clear? Now, we need to find the direction of this force. Okay, we need to find the direction of this force. So we use Fleming's left hand rule. So my first finger, okay, this is my first finger. So I'm taking my first finger in the direction of magnetic field, and magnetic field is acting perpendicular to the plane of the board and is directed inward, and current is flowing from Q to P. Okay, so my second finger, okay, this is my second finger, it is directed from Q to P, and the thumb, okay, stretched thumb is pointing in downward direction. So we have force F, okay, acting in downward direction. It is acting in downward direction. So direction of this force is downward, and we know weight, okay, weight of PQ, okay, also act in downward direction. So we have this, okay, we have force acting in downward direction, and we have weight mg acting vertically in downward direction. Now let us represent this, okay, concept or this figure in this diagram. Okay, so what we find, we always find that tension, okay, in the string acts towards the point of suspension. So this is the point of suspension, and the tension in the spring when current is in clockwise direction is T2. So T2 act in the spring in upward direction, and force on PQ act in downward direction, and weight of PQ act in vertically downward direction. So we have this. Therefore, what we can conclude, okay, from this particular case is that, okay, T2, that is tension T2, equals F, I'm writing in magnitude, okay, plus mg. Therefore, we can write T2 equals F is ILB plus mg. So we have this, and let us call it equation 2. Okay, so this is equation 2. So we have this. Now we are asked to find the change in tension. Okay, so I'm writing over here. So let me write over here. We have equation 1. Okay, this T1 equals mg minus ILB. So we have equation 1. T1 equals mg minus ILB. So we are asked to find the change in tension. Okay, therefore we can write change in tension equals delta T. Therefore, delta T equals T2 minus T1. So delta T equals T2 is ILB plus mg minus, and T1 is mg minus ILB. So let us simplify this. So delta T equals ILB plus mg plus mg minus mg, and we have plus ILB. So mg cancels out. Therefore, change in tension delta T equals 2 times ILB. So this is the change in tension. Okay. So this gives change in tension in the spring